Hello, future Ps. This is Wasim Asghar. I'm a licensed professional engineer in the US and Canada, and I've authored several books on the topic of FE Electrical and Computer exam and the PE Power exam. In this video, I'm going to handle a question that I received from one of my students during live training related to Kirchhoff's law. As you know, Kirchhoff's law, KCL, and KVL form the basis of circuit analysis, and they can actually be extracted from Ohm's law. Kirchhoff's current law is basically a law of conservation of charge, and Kirchhoff's voltage law is based on the law of conservation of energy. A lot of times I find students making silly mistakes related to KCL and KVL, and in most of the cases, it boils down to lack of fundamental understanding. In this particular session as well, you're going to see me break up the overall circuit into more manageable bite-sized chunk, and we are going to apply first principles in a stepwise manner. This is the approach that I take in my FE Electrical and Computer exam preparation program, as well as the PE Power exam preparation program. If you would like to learn more about my exam preparation courses, then please visit my website www.StudyforFE.com for more details. If you're not subscribed to the channel yet, I would really appreciate if you could click the subscribe button to stay up to date with the weekly content that I publish related to FE Electrical and Computer exam preparation, as well as the PE Power exam preparation. So without further ado, let's dive into the content. So let's say you have a resistor. Conventional current flow basically says that the current basically leaves from the positive terminal and ends up at the negative terminal. Or more accurately, the current flow happens because a difference in voltage, the potential difference or the voltage difference, such that the terminal with the higher potential basically is going to pump the current out essentially, and the current will flow from high potential to low potential. It's just like if I have the pen right in front of me, what I've done by raising the pen over here is increase its potential energy, correct? Right, guys? So when I drop the pen, it goes from high potential to low potential, correct? Under the action of gravity. It is not going from ground up by itself, correct? So the positive terminal is considered to be a higher potential. Negative terminal is considered to be a lower potential. So that's why the current flows from a high potential to low potential. Now your comment regarding electron current flow. In reality, it's not positive charges that are flowing, right? It is actually electrons that are flowing. So in reality, the terminal that is negative in polarity with reference to ground, I don't want to make it too complicated, but these positive and negative terminals are actually referenced to a common terminal, which typically is taken as a ground. If you have an excess of negative charges on the negative terminal, in reality, the charge carriers are electrons, right? In reality, the electrons are actually moving from here to here. When the electron moves from negative terminal to the positive terminal, there is a negative current flow, right? Electrons are going from here to here, right? So the way that we reconcile it is that if electrons are moving from here to here and they have negative charges, we can replace this with positive charges that are moving in the opposite direction. And the effect is practically the same. Do you guys follow that? Right? Does that answer your question? Okay. But, you know, we only deal with conventional current, which is from positive terminal to the negative terminal. All right, guys. Okay. Now, the KCL is based on the law of conservation of charge. It says that the sum of current entering a node is equal to the sum of current that's leaving. In this particular example, I have 3 currents that are injected at this node and 1 current that is leaving, so they better be same, right? So the 3 ions that are entering the node should be equal to the 1 I out. Very simple, straightforward. Now let us put this to use. Okay, I've given you some fundamental framework, and let's see how we can apply it, right? And typically within my program, the questions, the quizzes, the mini exams, the homework assignments that I present my students tend to be a little bit more difficult, more challenging. And the idea is that if you are comfortable with the more challenging stuff, hopefully, you know, logically, you should be even more comfortable with the easier stuff. Okay. So I'm asking you so one of the important things is that when you're doing circuit analysis problems, guys, you got to keep your eyes on the prize. Can you guys tell me what is the prize over here in this question? What is the prize? I naught. Make sense? I naught is the price. Okay, you got to keep your eyes on the price, right? I naught. Don't analyze this circuit for every voltage. Don't necessarily analyze a circuit for every single current or power gains and power drops. We got to be laser focused on what the question is asking. It's asking for the current flowing through this 2K resistor, which is identified as I naught. Not the current flowing through this 2K resistor, not the current flowing through this 2K resistor, not the current flowing through this 6K, this 3K, and so on. Is that clear? All right, guys. It is one of those things where students waste a lot of their time, energy, and effort, right? If they get overwhelmed by the question and they're like, okay, let me just, analyze this entire circuit inside out. That's not necessary. You may have to go through several steps until you get to I naught, but always keep your eyes on the price. Okay. So which point in the circuit qualifies as a node? We are doing KCL, so I'm going to help you write the KCL equations shortly. But which points in the circuit qualify as nodes? What do you guys think? Is this a node? Let me call them A, B, C, and D. A is a node. You guys are saying C is a node. What about D? What about D? A, B, and C. What about D? What's special about D? D and C are basically the same. You guys agree? Because there's no change in voltage. I don't have any circuit element, resistor, current source, voltage source, or anything. So I have C and I've jumpered it to D. The voltage VC is the same as voltage VD. Correct? So they are not a unique node. When I compare A with C, what do I have? A 2K. When I compare A with B, what do I have? A 3K. Correct? So B is also a node, right? What about B and let's say this point right here? I have a voltage source here. What about A and this point? I have a resistor here. Okay? Does it make sense, guys? So if I have to write KCLs, writing a KCL will give me a unique, set of equations. Writing a KCL here is going to give me a unique set of equations, basically, right? And so on. But writing a KCL at C and D is basically the same thing. Now, a very handy concept when it comes to circuit analysis, right? And let me know if I'm speeding too fast or too slow. I can adjust my pace. A very handy concept in circuit analysis is the concept of virtual ground. Virtual ground is just a fancy way of saying that I have a common point in the entire circuit with respect to which I am going to analyze the circuit. Okay, so you can see that in this circuit, if I select this as a virtual ground, it will make my life easier. It's just a common reference point, and it's a good reference point because a lot of branches, right, are connected to this. Can you guys see this? Does it make sense? Okay, I am going to assign it 0 volt. Okay, a common reference point, and then go about my business. And it will really help me simplify. So whether a question shows you a ground, identifies a ground right in your face on the circuit or not, you can always introduce a virtual ground. Okay. And you have to be consistent throughout and assign it a 0 volt. Where should I write KCL equations? Where should I write the KCL equation? On the nodes. as we discussed. Is there only one correct assumption for current direction? What do you guys think? Can you assume a certain direction for current and then go about it and then solve it and then hope that things work out? Or you have to have your assumption 100% accurate from the get-go? What do you guys think? Quickly, help me out here, guys. You have to start out with the 100% correct assumption from the get-go for current direction? No. You can assume anything. Okay? You can assume any direction for current as long as your assumptions are consistent with the equations that you write. Okay? What is the worst case scenario if your assumption was wrong? What are you going to end up with? What do you think? What will happen at the end? When you analyze the entire circuit and you realize your current direction was actually wrong, what is the worst thing that can happen? Quickly, let me know. Wrong sign, not a wrong answer. And guys, I'd appreciate if you could use drop down everyone, okay? Wrong sign, Megan, you're right. And how do you handle it? How do you handle it? So your magnitude of the current will still be correct. Okay? The sign will be opposite, and the sign is telling you that in reality, the current was flowing in the opposite direction. Is it a big deal? Is it a big deal? No. You just go back to the drawing board and you change the direction of current. The magnitude is fine. And whichever currents end up with the negative sign, you just flip them. That's it. And that will automatically rectify your circuit analysis. Okay? Is it clear, guys? All right. So in my program, I have multiple calculator tutorials as well for FX115ES and TI36X Pro. I can give you guys a demo later on. And, system of linear equations you can easily solve. The math is not the key over here. It's the circuit setup. That is the key. So let's do the setup. Okay. How do we go about doing the setup? So can you guys see that if I throw a virtual ground over here, do you guys agree that if I call this as B, right, node B, that the current I naught is equal to VB minus 0 divided by 2K? Okay. What happens if in the exam I have two answers with the same magnitude but different sign? How to approach this? Okay, that's where, Hector, that's where you have to go back to the assumption, to the circuit. Okay, let me solve this circuit first and then I think it'll be a little bit clearer. Okay, hold that thought and we'll come back to it. All right, can you guys see how I wrote this equation? VB minus 0 volt divided by 2K. Everyone agrees. Current is flowing downwards. Current always flows from a higher voltage, okay, which better be B in this case, right? VB minus 0 volt. 0 volt is a virtual ground divided by 2K. You need to be able to write this equation in your sleep when you're doing circuit analysis. And this is that basic concept of delta V, that the current flows from a higher potential to a lower potential. In this case, we have fixed, because this question has fixed the direction of current, and the question is saying that I naught is flowing downwards, right? If I naught is flowing downwards, then VB better be a higher potential, minus 0 volts divided by 2K. Everyone is fine with this equation? Any issues? Let me know. Cool. All right. Okay. Then at node A, right? If I throw a virtual ground here, can we write a KCL at node A? And are there any correct, right, wrong, better, worse assumptions? I'll give you some rule of thumbs that will most likely always result in the right assumptions, but even if the assumptions are wrong, it's not the end of the world. If I have a voltage source, one end of which is 0 volts because it's connected to 0 volts, can you guys tell me what the positive terminal is going to be for this guy? So V plus the positive terminal of the 9-volt battery minus the negative terminal of the 9-volt battery is equal to 9 volts. You guys can see this? Everyone can see this? It's not rocket science, guys, right? The difference between the positive terminal of the 9-volt battery and the negative terminal of the 9-volt battery is 9 volts. Correct? Yes? Now, I have grounded the negative terminal, which means that this is 0 volt. Correct? That basically means that V plus 9 volt superscript is equal to 9 volts. So that basically means that this is 9 volts. Clear? It's all first principles. There's no rocket science, no memorization required. One of the frequent questions that I get from students is that, Wasim, do we have to memorize, right? Common question in FE electrical and P power. Trust me, guys, you don't have to memorize. If, and that's a big if your fundamentals are strong. And that's what I aim in my program. I tell my students, regardless of whether you were a 2.5 GPA student, 3.0, 4.0, right? The way we comfortably pass this exam is by having a strong grasp on the fundamentals. And this is just simple voltage difference equation. Okay, now if I have 9 volt here, and this is the only voltage source, do you think most likely this voltage source is going to be pumping current into the circuit, or is the current most likely being pumped into the voltage source? What do you guys think? Most likely the voltage source is pumping current into the circuit, right? So is it a fair assessment assumption for me to assume that the direction of the current from the voltage source to the VA is going to be like this? Reasonable assumption, I think. Correct? Okay. Now, this is the only source of power in this circuit, right? And we have a ground, right? We have a ground, common ground, virtual ground, right? Isn't it reasonable that if the current is entering in this node, and if this is 0 volts, then the current, if you just imagine gravity even, is going to fall down. Correct, guys? Right? And it's a reasonable assumption. I don't know whether it's going to be a correct assumption or not. Okay. I'm not too rigid about it. I'm not too hung up, right? Whether this is going to be right or wrong. I'm just making some educated guesses. Okay. Clear? So that's the direction I've assumed for the 6K, right? And I'm thinking out loud and helping you guys basically walk through my thought process. And then the current that gets pumped in by the 9-volt source, some of it goes through the 6K resistor. Is it reasonable to assume that the remainder will go through the 2K resistor? Correct? So now, if we are sitting, standing, and observing at node A, can we write this equation that the current is coming from 9 volt to the VA divided by 3K? And that's basically this current. Is it making sense? Can you guys relate to this equation? Understand this equation? Any doubt, any challenge? So that's my current in, right? What is my current out? My current out is VA minus 0 divided by 6K, right? VA minus 0 divided by 6K. So that's this guy, right? Do you guys agree that that's the case? VA minus 0 divided by 6K, correct? Okay. Any issues with this, guys? No. And then the current that is passing through the 2K is simply going to be VA minus VB divided by 2K. That's this guy. Correct? Right? Now, is there any rocket science involved? Is there any, high level, extreme, complicated concept that I introduced? while writing these equations? Just first principles, right? Fundamentals. Correct? Okay. Now, the important thing, guys, you need to remember this. Once I have made assumptions, set the directions or the currents, okay, I have to respect them and continue with them throughout the circuit analysis. And let me explain you what that means. If I have assumed that the current is going from VA to VB, I could have assumed the other way as well. Doesn't matter. In fact, you guys can go ahead and solve this question with VB minus VA. Okay, it doesn't matter. The important thing is that when I move on to writing the equation at node B, I cannot make a second assumption or reverse my first assumption and flip the direction of current between A and B. Let me repeat this one more time. As you work through the circuit analysis step by step, the degrees of freedom that you have in deciding whether the current is entering or leaving get frozen. Clear? So if I have frozen the direction of current from VA to VB while writing the nodal equation KCL at A, I have to respect that. So when I move here, if casually, right, without having any understanding, okay, amateurly, if I flip this, guess what? I'll get a wrong answer. This is where the remaining 25% of the mistakes are made. Okay, so at node B, I have to assume, in fact, continue my assumption that current is flowing from A to B. Is that clear, guys? Okay, very important point. Okay, now if the current is entering from VA to VB, right? When we're writing the nodal equation at B, we actually don't care about what else was happening over here. Our focus, okay, the center of attention, the center of the world is node B. Now, if one current is entering node B, and if I have a ground over here, like gravity example again, isn't it reasonable to assume that the current will flow from B to ground? And we already know that this is I naught, so this is already flowing to ground. What do you guys think? Does it make sense? Yeah. I think it's a reasonable assumption. Correct? Right? You can assume it the other way around as well. You'll still get the right answers if you know what you're doing. Okay? So, VA minus VB divided by 2K, and this we are inheriting from our previous assumption. Correct? So that's my VA minus VB. Okay? That's this guy. Okay, this is now current in. Then I have VB minus 0. That's basically this to this. Make sense, guys? And then VB minus 0 divided by 2K, which is basically my I naught. All good? Any issues? All right. So when should we stop writing these equations? There should be some sort of an end game, right? Should I just keep on writing equations just for the sake of writing equations? Or should I know when to stop, right? When you have written equations, as many equations as the number of unknown variables in your circuit, that's when you stop. So let's see how many unknown variables I have. Okay. So I have I naught, one variable. I have VB, another variable, VA. So I have how many variables here, guys? 3, correct? How many equations I have? Unique equations. 3. Will it do the trick? Yes. So in your calculator, and I have tutorials in my program, TI-36, I also have Casio lying around here somewhere. That's actually my favorite calculator, right? It was somewhere over here. Yeah, here it is. Okay, Casio. They have a new model of Casio. Just make sure that on the NCS website, you do check the approved list of calculators. 3 equations, 3 unknowns. Takes 30 seconds to punch these in and get the results. Okay? Or you can do mathematically, manually, right? Back substitution, matrices, Kramer's rule, so many different ways, right? The easiest one is, guess what? Calculators, right? So spend about 5-10 minutes learning how to punch in the equations and getting the results. So we have 3 equations with 3 unknowns, and that's where we're going to stop, and it's going to give me the results, right? So when I punch in the numbers, right, I get VA as 3.6, VB as 1.2, and I naught as 0.6 milliamps. So Hector, let's address your question, right? You were asking that in the end, if you get a negative answer, right, and options A, B, C, and D are giving you a negative answer. One is, let's say, 0.6 milliamps, correct? Are you there, Hector? Just type up yes. Okay. And let's say the other one is minus 0.6 milliamps, correct? Which one of these is right? What do you guys think? That's a loaded question. So thanks for asking that, Hector. Which one of these is right? What do you guys think? B? Yeah? What do you guys think? B or C? Okay. So the correct answer is that just by looking at a number, right, you are not always 100% sure about the direction. So let me do this. Okay. Imagine that the question actually had shown the direction as opposite. Okay, let me just frame this a little bit differently. And by comparing and contrasting, it will be a little bit easier. Suppose that the I naught was shown like this. Okay, and suppose that the answer was 0.6 milliamps. Okay, are you guys with me? All right. Now, what ends up happening over here is that you actually have to look at the circuit, correct? Now, if I naught pointing upwards, right, resulted in 0.6 milliamps, right, then this is the correct answer. But, and listen carefully, please. But let's say if the question had indicated I naught as 0, if the person had indicated I naught as pointing downwards, correct? Your direction, your assumption, please listen to this carefully, guys. You assumed, for whatever reason, doing your circuit analysis, your assumption of I naught was pointing upwards. Okay? The answer that you got was 0.6 milliamps. Based on your assumption, you can assume anything, as I told you. Pointing upwards was 0.6 milliamps. And now the choices that you are given are 0.6 milliamps and minus 0.6 milliamps. And in the original circuit, they have I naught pointing downwards. Are you guys following me? This was your assumption. You decided to flip that. And you ended up with 0.6 milliamps pointing upwards. The way they've drawn their I naught is downwards. If you like this video, then please don't forget to subscribe to this channel. Feel free to ask me any questions in the comment section of this video below. You can find tons of success stories of my FE Electrical and PE Power students over here. And if you want to learn more about preparation of FE Electrical and Computer exam and the PE Power exam, then check out these playlists over here. Thanks for watching, and I'll see you soon in the next video.